When an object is displaced by a force, we say that the work has been done by the force. But what exactly is this work done? What does the force do to the object that we call work? Just as we have bank accounts, objects have their energy accounts. And just like bank accounts, energy can be transacted to or from these accounts. There are only two types of energy transactions in physics: heat and work. Work is the energy transaction via force, and heat is the energy transaction due to temperature difference. Let's define work. Work is the energy transferred to or from an object by a force acting on the object. Energy transferred to the object is positive work, and energy transferred from the object is negative work. The SI unit of work is joule, and it is a scalar quantity. Here the term transfer can be misleading. The transfer of energy is not like a material flow into or out of the object. Rather, it is like an electronic transfer of money between two bank accounts. The number in one account goes up while the number in the other account goes down. But there is nothing material flowing between two accounts. Now the question is, how can we calculate this energy transferred by the force? In physics, there is an expression for it, and I'm going to derive that expression for you. Let us consider a bead that slides on a horizontal wire. Suppose we have this horizontal wire stretched along x-axis. There is a bead sliding along this wire. Let m be the mass of the bead and F be the force acting on the bead at an angle theta with the x-axis that accelerates the bead along the wire. We can draw the component of this force along x-axis. This is the x component of the force, and we know it is equal to F cos theta. By Newton's law of motion, we can write Fx equal to mass into Ax. Let's call it equation 1. Ax is the component of acceleration in x direction. Now, due to this acceleration, the velocity of the bead will increase. Suppose the initial velocity of this bead is v0, and its velocity increases from v0 to v as it moves through a displacement of d. As the force is constant here, so the acceleration will also be constant. So we can apply the equation of motion with constant acceleration on this bead. If we apply the equation of kinematics, we can write v square equal to v0 square plus 2ax into d. I have applied this equation of kinematics in x direction. If we multiply this equation with half m, we will get half mv square equal to half m v0 square plus max into d. This half mv square is the final kinetic energy, and this half m v0 square is the initial kinetic energy of the object. So we can write this as k final equal to k initial, and this max, from equation 1 we can write this max to be fx into d. Let us bring ki to the left side. Kf minus ki equal to fx into d. Suppose this is equation 2. Now the left hand side of the equation 2 is the increase in kinetic energy of this bead. This increase of kinetic energy can be only due to the energy transferred to the bead by the force. So we can replace the left hand side of this equation 2 by the work done by the force. So let us replace this. We get W equal to Fx into D. Now in place of Fx, we can write F cos theta. W equal to F cos theta into D. We can write W equal to Fd cos theta. W equal to F dot D. This is the expression for work done by a force, dot product of force and displacement. So the conclusion is, Work done is the energy transferred to or from an object by a force acting on it. And mathematically, it is given by W equal to F vector dot T vector, displacement vector. So the work done can mathematically be defined as the dot product of force and displacement. This is the formula for work done.